Edlin. He is currently a geologist at Iodine Resources. Got a minor in chemistry or bachelor's of geology with a minor in chemistry from Baylor in 2009, as well as a master's in hydrology from the Colorado School of Mines in 2013. He is a registered professional geologist in the state of Wyoming. And David's been a geologist for IFINA for 12 years, in which he has researched economical locations for interest in iodine extraction. During this period, he's primarily focused on assets in the Anadarko Basin in western and central Oklahoma and the Permian Basin as well. He has researched assets in the Marcellus of both Devonian and Utica, Barnett, Bakken, Uinta, and Paradox Basins, Monterey, Greater Green River Basin, and the DJ Basin. He has worked with existing oil and gas operators and midstream companies in these areas of interest to access water samples for iodine analysis through titration methods. Upon finding desirable iodine concentrations, he works with potential partners to better understand brine availability, longevity, and infrastructure, as well as reservoir analysis to contribute to IFINA's economic model for manufacturing facility placement. Additionally, David has partnered with OCAST and Northwestern Oklahoma State University to run an internship program for the last 10 years as a primary mentor. So with that, I will turn it over to you guys and let's take a look. You're gonna. Oh yeah. Share. Right. It's like share.
Wait, it's not the same screen. It's not the same screen.
Yep.
Perfect. All right. Hello, everyone. My name is David Edlin, and this is Andrew Gordon, and we're going to be talking about iodine and what we've been working on here in the Anadarko Basin. We are with Iodine Resources, and we've been operating in Oklahoma for about since 2012, and we are going to go over the outline of first the history of both iodine and iodine here in Oklahoma. Then we're going to talk about our water sampling program, as well as the heat maps that we're generating from these concentrations we're getting in different formations throughout the Anadarko Basin. And then we're going to talk about the exploration process for the subsurface work that we're doing, and pretty much go on from there on our conclusions and what we're focused on in the future. So talking about the iodine industry, the iodine has been studied, and it has been pretty much harvested since the late 1800s. But it kind of dwindled off in the 1920s. In the 1970s, Woodford Iodine Company started up, and they started producing out the Woodford Trench. In the 80s, the Iochem Company started to do the same thing over there, and they're drilling their own brine wells to harvest the iodine. And then we showed up in 2012. But as far as globally, the global demand is about 40,000 metric tons of iodine. As of 24, there has been a steady increase of iodine usage within an array of industries. And so the growth has maintained a 3 to 5% increase year over year for the last 10 or so years that I've been a part of it. Historically, Chile has been producing about 65% of the world's iodine. they are mining in the Andes for copper and silver and those precious metals. But in the tailings, the iodine's in the caliche, and so they've been washing out the iodine from there, and they're able to produce 65% of the world's iodine. Japan does about 25% of the world's iodine, and they're getting it from their gas fields over there. And then the rest of the world does 10%, with North America doing roughly 5%. And as far as iodine goes, there's no 800-pound gorilla in the room that dominates the market. Iodine is traded as a commodity on the stock market. And so iodine's used in different industries like agriculture for pesticides, fertilizers, cosmetics, construction materials, pharmaceuticals, things, technology with touch screens and films. And so there's a lot of different uses, and year over year, people are finding new ways to use iodine as a cheaper replacement for the existing materials that they are using in the process. So it's a pretty fairly even balance of iodine usage throughout the world in those different industries. Iofina, we started off in 2008 as a natural gas company in northern Montana, and that turned into a dewatering project. And to save costs, because the natural gas prices were plummeting, we're looking for ways to offset the expenses we're accruing. And essentially, we found iodine in the water, and we got into iodine business right there. Found out we're making more money with iodine than we were with natural gas, so we made the pivot at that point. From Montana, we built a plant down in the Barnett in Texas, outside Fort Worth and Burleson. And that was in 2010, 2011. In 2012, we got our first plant in the Alva area of northwestern Oklahoma. And from there, we've been building a few plants since then. And so we currently are the second largest iodine producer in North America, and we're hoping to become the largest here in the next year or two with the new plants that we're bringing online. We have 7 active plants, with an 8th one that will begin operation here in the next month or two. And we are looking at continuing to grow by a couple more plants year over year for the next 5 years. We use a wet iosorb technology, where the difference between Iofina and Wick and Iochem, the other two companies, is that they drill their own brine wells. They have a clean source. They produce it, and that's how they're operating and harvesting iodine. For us, we recognize that oil and gas has a bunch of holes in the ground. They're producing a lot of water, so let's just piggyback off of them, partner with them. They make a little extra money. We're able to produce the iodine, and both parties are able to be economical on it. And with our technology, we are designed to handle the oil-filled water, so all the extra junk that comes in the water with it, we're able to help them clean it up and run the water through our process, and we're able to harvest the iodine from that point. Within this partnership between Iofina and the oil and gas operators, the midstream companies that we partner with, is typically we build off of their SWDs, but we're also able to tie into the pipelines, whatever works best for a good aggregate, consistent volume for an incoming stream. Iofina, we do pay all the CapEx and OpEx to build these facilities. We recognize that we're the iodine guys. The partners are the oil and midstream guys. They have their job. We have our job. So we handle all the land and legal. We build the buildings, the batteries, all the equipment we need to operate. We operate the facilities 24/7, 365, and we harvest the iodine. In the process, we do add extra security, add extra help for the partners we're with in case there are problems on that side of the boundary. But Iodine is a controlled substance, so we are licensed with the DEA. Right. We are licensed with the DEA, and we have to have all of the iodine that we do produce stored securely and safely in between production and shipments. The chemicals that we use are typical throughout the industry of acid, bleach, caustic, and peroxide. On the partner side, they continue doing what they're doing. They help us try to maximize the incoming volumes and concentrations, but they are receiving the royalties or whatever contractual agreements that we have in place for their portion of the shares. And for operations, we do add an extra benefit because oil, hydrocarbons, they do clog up our tower. And so we need to remove as much oil as possible, which helps out the partners because they want to keep the oil. We don't want it. And we have the water cleaned up a little bit better, and then we return the water back to them at the pH level that they're needing. Here's a process cartoon of our facility. Over there on the red scoop, that's the iodine that we produce. It's called a cake or a flake. It's a sandy material, purple metallic hue color. And that's the iodine that we produce, and it's used in everything but consumable pharmaceuticals. The little buckshot that you see down there is called pearl iodine, and that stuff is just a higher grade that is used for pharmaceuticals and medications. So in our process, when you have water coming into the system, and we loop the brine water from, let's say, a SWD tank battery into ours. We treat the water, clean it up, remove any junk, and we manipulate the pH to weaken the iodine bond. We throw it through our tower, which has a bunch of packing, and from there we are able to blow over the iodine into our absorption column. And do we have the laser pointer? No, I can do that.
I can't figure it out. Yep. Might not be able to.
That's okay.
It was easily.
Anyways, you have right there, the middle purple column is the absorbing column. At that point, we are concentrating up the iodine within our facility. And once we hit a specific level, we send it over to our crystallization. We crash it out, and that's where we get that iodine cake over there with the red scoop. And that's ready to ship out directly into the market, or we send it over to our sister company in Kentucky that puts the iodine different derivative for the customers. From the water that's falling through the tower, that's where we clean it up, neutralize it, and return it back to our partners. And from there, they're able to dispose it, or they're able to reuse that same water for whatever purposes they're designated for, like fracking.
And just to the cake versus the prill, the purity, I mean, the cake itself is 99.3-ish% pure, 3 to 5% pure. And that prilling process, it basically just superheats it and removes that last 4 to 0.5%, which is the kind of leftover water that we can't get out ourselves. That creates that buckshot, and that gets it to that 99.9% pure iodine. So the iodine that we're producing is, for all intents and purposes, pure iodine. There's just a little bit of impurities left over that's in that water weight.
Exactly, and the infrastructure that we need to create that prill is it's a completely different process, because we are having to deal with high pressures and melt the iodine to get that extra 0.5% purity. And so at a certain level, we are looking into getting into that part of the business, but for right now, we've just been focused on the flake. And so here, going over spot pricing of the current prill price is about $60 a kilo. You see here on the fifth bullet point. And then flake is sold at about 15% reduction of that overall cost. You see on the graph From 2018 to 2024, iodine has been steadily increasing with a decent jump from 21 to 24. Sorry, 23. And then the prices have been hovering at that same level since 23, and we're projecting that it will continue through 2025. The other elements of interest like manganese, lithium, bromides, though lithium is always a hot topic because it did spike so much in 22, but the prices have come back down. So making it economical is difficult, but we are still interested in all these elements outside of just iodine. But these are all, just like iodine, dictated by the stock pricing.
Are all these coming out of brine? You lifted them and all that, you can get them out of brine.
You can get them out of brine, but that graph was just pointing out the market prices.
And then just to point it out, I mean, there's very few companies that are extracting elements from, especially oil and gas brines. And then the ones that are still mostly in their pilot phases, especially on the lithium side, besides the big projects that are happening, you know, in Arkansas or northern Louisiana. That's the big one. They just, 6 months ago or so really went into operations. But most of the other elements aren't currently being at least economically extracted. Iodine's the big one, and then lithium, again, everybody's talking about it, but there's not a lot of at least smaller players. There's big Exxon's doing it. So, right. But we do try to track all of the economic elements just so that we have our database when we do sample, and Dave will talk about this. When we do sample, we're always sampling for more than just iodine.
Mm-hmm. So running through the bench process, from here, the best part about us sampling your water for iodine is that it's free to you. We absorb all that cost because it helps us figure out where we can find locations of interest to build a facility versus where not to focus on. And so whenever I get water samples from you guys, we're definitely interested in the iodine concentration, but we're also looking into the pH, the temperature at the time of collection, since that plays a factor within the facilities. And then just the visual aspect, if there's a bunch of stuff in the water, what would that take? We're also looking into brine characteristics and other factors that are now noticeable indicators that we need to include within our models. But as far as sampling goes, I take the sample into the bench. I run a titration method. You're just manipulating the pH levels to weaken that bond so you can separate the iodine out. And then whenever it comes out, this is a high concentrated sample, roughly 400 or 500 ppm. And you get that pretty ruby red color at the bottom. From there, I'll titrate it and get that iodine concentration. And then that's what we're doing at a well level basis and aggregate point level, and just trying to figure out where to go. Here's some pictures of similar samples, but with lower iodine here. On the left, you get this moderate level. This is about a 200 ppm sample. And over here, you're at about 90 to 100 ppm sample. It's a lighter pink. And so the darker ruby red color, that gets me excited. With the sampling program, we have a couple phases, but to start, whenever we do get interested with you guys, there's some data needs that we're needing. And it's mainly based on volumetrics and concentration. So the volumetrics you guys would have, and would ask for up to a year of historical data just to figure out that trend of what a specific location would look like. Is it piped? Is it trucked? What are the pressures you're dealing with within the pipeline, within the downhole of that disposal? What are the limitations that could manipulate some of those factors to model? What we typically look for is, on a general rule of thumb, is 15,000 barrels a day at 150 ppm. you don't, you can definitely get by with lower volumes, say 5 to 10,000 barrels at higher concentrations. And you can also get by with higher volumes with lower concentrations. So we're looking at a total kilos of iodine produced per day is what we're trying to get to figure out on that economical level of facility placement. So on phase one of a sampling project, we can either send out kits, and these are 1 or 4 bottle sample kits that we send out to you. We're looking for anywhere within the process that is not directly behind a chemical injection port, because that would mess up my sampling. But as far as getting a good raw brine sample, we'll get that, or we'll collect it in person, and the turnaround is roughly 1 to 2 weeks. If there's not enough iodine there, again, it's a free test for you guys, and I'll let you know what the concentration is and say thanks, but no thanks. But if it is economical, I'll say thanks. Here's the concentration. Let's talk more. Let's go into the next level of sampling, which we would like to establish a weekly sampling and start to build that trend so we can figure out the lows and highs within the stream, and we can quantify the concentrations for our modeling purposes. From the continuous sampling, that's where we'll monitor the characteristics of the iodine targets, the thresholds of the brine characteristics. That's where our chemical engineer will start looking at other stuff within the water that could cause us to use higher chemical consumptions within our facility. We'll monitor the pH and pretty much all those factors that goes into operating the plant. Here's a map right here that demonstrates where our current facilities are. The red stars are our active plants. We have 2 in Woods County, 2 in Alfalfa County. That's our original field, with IO2 being our first plant in Oklahoma. Then we moved over to south of Arnett in Ellis County. That's our IO8 plant, and that's in the Cherokee and Cleveland formations. We're operating out of the Mississippi formation up in the Alba area. And then our 2 newest plants are down here in the stack in Meramec. And that's IO9 and IO10. And this blue star right here is our newest plant being constructed, which should come online here in the next month or 2. And of course, we're looking at there's still a lot more locations of interest to build, but this is where we're currently operating. You want to take over from here?
Sure. So yeah, Dave gave a great overview of kind of how our business operates, because I know lots of people are interested in how it works and what we're doing. So now we'll get into some of the technical geology side a little bit. There's very little research that's been done on iodine enrichment within brines, and even just the iodine that's been extracted out of the Woodford Trench and the exploration that's been done historically. So a lot of the work that we're doing is kind of starting from the ground up. These maps, the one that I'm showing right now, is basically from all the 1,000 plus samples, over 3,000 samples, either at the wellhead or at some sort of aggregation point. So this is basically flattened across all formations. It's not specific to one formation, but you can see the Woodford Trench that jumps out pretty exacerbated over there through Woodward County. That's where it was originally found. You get hits of over 1,000 ppm easily across the Woodward Trench. And so that's a completely different model than what we're doing. We're looking for those lower concentrations, while we will still take them if they're higher. The model that we're looking at is trying to use the produced water, which generally has a little bit lower concentrations. But you can see where we've got plants currently operating on this map, and then the areas that look to be ideal candidates for future locations. And again, just because there's concentration doesn't always mean that there's the volumes that are necessary. So this map really just kind of gives you an idea of where we've got some decent hits, but we'll start to look at those individually and look at them more on the formation level going forward. So again, like Dave said, we started up in Alfalfa County in the Mississippi formation. So you can see here, you've got a nice structure that seems to be trapping and enriching in the iodine concentrations anywhere from 100 to over 400 ppm. The places where we do see those higher concentrations are generally from one single well, and it's not continuous throughout. Again, we're operating on an aggregate basis, so a lot of these volumes of water and then concentrations get averaged out to a lower volume. But as we move forward, we'll look at some of the geology right now. We're just going to keep running through these heat maps. But again, this is in northern Oklahoma, the Mississippi Formation, where we first started, and then moving out to Ellis County. This is really of interest to us with the big uptick in interest in the Cherokee Formation. So we've been operating out there for quite a while. And again, this is kind of a story of, while there are some really good concentrations as you move east into Dewey County, we do see a drop off in volumes of water to where it makes it not quite operationally feasible for us, at least at the time of original sampling. But through Ellis County, even at 100 to 200 ppm, the volumes are there for us. Where we've been focusing lately is down in Kingfisher and Blaine County in the Meramec Formation. This is an area that lots of activity has been happening and has happened in the past and going forward. So you can see our two most recent facilities. This is IO9, this is IO10, and then our newest facility that's set to come on in a couple of months, IO11. Lots of really good information coming out of here. We've been sampling really hard over the last couple of years. We've got data points all through Kingfisher and kind of that southeastern portion of Blaine County, and then as well down into Canadian County.
What's the red line?
That's the Canafault. Sorry to put that in there. So that's just me kind of drawing it in from the USGS data set, that shapefile. And so, it definitely correlates with that low that kind of moves through there. When we first plotted up this data, we didn't have any of that structural data or any of that fault data put in there. And so we were scratching our heads. You'll see in the next slide, the Woodford Formation definitely is lower in concentration of ppm. And so it seems that that fault's probably connected to water that is coming out of there and cooling the concentrations a little bit. But that's still kind of something that we're working through on our end, trying to fully understand where that water is coming from. Is it enriching in place? Was it enriched and then moved through the system? So yeah, that's still part of what we're doing. But whenever we threw that Canafault on there, it lined up pretty much perfectly with that low spot through the middle of those townships. And so then again, you can see here moving into the Woodford Shale, a pretty big shift in concentrations across the same area. And so again, these maps are all based off of wells that are producing in these formations. So while they're overlapping the same area, that previous map was all Meramec aged. So Osage, Meramec, upper and lower formation production wells, and then this is all the Woodford wells. So you see quite a lower concentration of iodine in the exact same area, just based off of producing formation. We do see it start to tick up as you move further to the south in Canadian County, and that's something that we are investigating. It's a small data set that we have down in that region of the state, but we are interested to see, as you can tell, upward of 200 ppm is definitely something that we always are interested in seeing. So now trying to look at it more in the subsurface, just doing some regional mapping. This is looking through that Kingfisher, Canadian, Blaine County area. looking at the Mississippian aged rock, so upper, lower Meramec, the Osage. You start to see a little bit of a trend where you've got a little bit thicker, especially the Osage to the west. You see it again to the north. When this was first made, it didn't realize it was cutting right through or right around that fault. It's work that I need to go back and look at, but you see this trend both here in Kingfisher, where you have the thicker Mississippian strata, the higher the concentrations. You're starting to see it's not a direct correlation, it's kind of a general trend, but I think that there's a lot to be said for the carbonate factory and some preservation of TOC. There's, like I said, there was very little literature research on iodine enrichment within the brines. And modern day and historically, seaweed is kind of the highest organic organism that retains iodine. That's where iodine was first found back in the 1800s, and how they originally extracted iodine. To begin with, they would burn that iodine, and then the ash itself would be enriched, or burn the seaweed, and the ash itself would be enriched in iodine. And so between the carbonate factory and some sort of preservation of possibly seaweed or another organic organism, it seems like that might be the case. Again, we're really early in this research on our end trying to figure this out. So we'll continue to move through some of these hypotheses as we go forward. The next set of maps is just looking at the upper and lower Meramec with the overposted concentrations. And I don't have the scale on here. I'm sorry for forgetting to update this map, but the bubbles or iodine concentrations, with red being higher in the 300 plus, and then the greens kind of being in that 100 to 200 range, and then there's smaller ones that are the lower concentrations. As you map out the net, so clean gamma with porosity, you start to see a little bit of a correlation where as you have fluid flowing through that rock, it is able to possibly enrich, either washing off iodine that might be in the pore throats of that rock, or iodine within the rock itself. We have done one core study, which we'll talk about, and there's not a direct correlation measuring iodine within the rock itself. So we're going to continue moving down the path of trying to understand geochemically what's happening in the rock itself with iodine. But I'll repeat myself again and again. We've still got more questions and answers as we do this research. And so going back up to the Alva field area in Alfalfa County, we did look at 8 different Mississippian cores. We grabbed 2. These were the SWD wells, but there are offset wells right next door to these SWDs, which are the SWDs that we're using as our feedstock. So in this area, it was greater than 200 ppm for those 2 red wells that we analyzed core from, and then we looked at 3 cores that we called in a moderate area, which was somewhere between 100 and 200 ppm. And then we also looked at 3 cores, the blue cores, 1, 2, and 3 that were in cold areas of less than 100 ppm. And we just wanted to look at the facies, understand kind of what was going off, because you can kind of see that there's a pretty sharp knife's edge through here in this field with a nose that moves to the northeast kind of. And so just looking at another cross section, got a strike and dip cross section moving through the area. Again, that's kind of where you see the overall Mississippi thicker right through the middle of this northwest southeast trend. And that correlates with, as you move from the northwest to the southeast, it thickens a little bit right as you get to your highest concentration wells of iodine. You also see that trend moving to the southwest. So again, working on the hypothesis that there's a correlation between carbonate factory and or organic preservation through these rocks. And so the more you've got, the better chance you've got for enrichment in iodine. And so just a few pictures of the cores. I'm sure anybody who's worked these fields are familiar with the different facies that we encounter. And so again, just the biggest thing that we noticed was both the increase in biodiversity within the cores and the upper facies of the Meramec, where the wells were landing and producing from, versus looking at some of the cores that were further out, a quieter depositional area where you've got more lime, mudstone / shales, and less porosity, so less chance for fluid to move through and enrich with iodine. And this is kind of a summary, just looking at it more on that Blakey environmental map and where it falls within the basin, the type of things that we were seeing with the crinoids and the bryozoa versus the mudstones in that lower ppm area. It'll be nice if we can get back there and look at that rock again, spend a little bit more time. Again, we took a few core plugs, and so we sent those off, got them analyzed. There's not a lot of labs that look for iodine, so we had to work with them to figure out, they had to get their own standards. It was just completely new to pretty much everybody that we talked to. And so, the hope was that we would see iodine in the rock kind of correlate, maybe not in the same scale, but at least moving in the same directions. You can, in some places, see where higher iodine in the brine correlates with higher iodine in the rock, the highest being 6 ppm versus 300. It wasn't quite there. The one thing that did kind of jump out is looking at one of the wells with the lowest concentrations of iodine that moves out way into the cold area. It was pretty much all that kind of lime mud. Is a much higher dolomitization, which again kind of points back to fluid not being able to necessarily move through it, or there's some sort of interaction that maybe doesn't preserve iodine whenever you've got dolomitization happening. So again, a lot more questions than answers. So if anybody's got any thoughts or ideas, I'd love to talk to you guys afterwards. I'm not a true geochemist. Dave is more than me, and we've got a chemical engineer, but we're working at this and putting our best research hats on. We're looking to partner possibly with universities to put a little bit more effort into this going forward. So if you know any students that might be interested in a research project, that's also something that we'd be interested in doing. So in conclusion, iodine's been produced for over 50 years now in Oklahoma. But for the longest time, it was really just a couple of big guys doing it in the Woodford Trench. Since then, there's been a couple of people that have said they're going to do it, but we're out here actively producing with 7 facilities and more on the way. And we're not limiting ourselves to just Oklahoma. We're looking to expand into other basins as well. But the thing that we see is just the large opportunity of wastewater that all of these operators have to deal with, which, for all of industry's history has just been a cost to them, is now becoming, with both lithium, but, as we see it with iodine, a way to now make a little bit more money. We pay a royalty. It covers some of those LOE costs. It reduces operators' expenses. So pretty much everybody's making money. We don't ask for anything from the operators other than just let us borrow your water. And so, Oklahoma having a rich history of iodine, it's still where we're putting a lot of our effort into. But we're still developing all of our exploration models and techniques. There's no way, there's no known, correlation. People ask if chlorides and iodine are related, but there's not. There's really, at least for what we know now, there's no water chemistry component that correlates to iodine that's been measured kind of historically. And going forward, I think the big thing that we're going to start focusing on is using handheld XRFs. It's been used a lot in critical mineral research in sedimentary rocks and has proven to be a useful way of exploring. The thing that really helps out there is at that scale, especially in critical minerals, you see enrichment in centimeter type beds. And so the same thing might be happening with iodine. And so taking a plug, you're bound to miss it with just a 1-inch core plug. Whereas if you can run a handheld XRF that's been tuned to an iodine standard, you might be able to catch those thin laminations and then possibly grow that exploration model a little bit better. So with that, I think that's all the slides we have. So if anybody has any questions, let us know.
Yeah, are there radioactive isotopes of iodine that we encounter?
Yeah. That's a good question. So we haven't dealt with anything like that. In Barnett, we were dealing with norms in the water, but as far as using radioactive isotopes to measure the iodine, we haven't approached that one. That's a good thought.
So are you telling me that the isotopes don't exist, or they just haven't been looked at or detected?
I have not looked at that. We have not looked at that yet. Essentially, the instrumentation has been difficult because whenever you send off these samples to the third-party labs to try to confirm what you're doing, you get a lot of false positives, especially with mass spec or SQ. Those can read other elements easier, but with iodine, it always gets either too high or too low, and I can't reproduce it. With the titration method, that does mimic what our facility is doing. So if I'm getting a 100 ppm sample at the bench at this specific location, if we had our facility there at the same spot, that's essentially what we'd be producing too. So that one works. But as far as using these other technologies, like what Andrew was saying, whenever we are working with these other companies, we're either getting extremely high numbers or we're getting nothing there, but it's hard to find a good standard for iodine. So
Another question I had was, when you collect the water, is that only during times of oil and gas production?
Say that again, I'm sorry.
When you collect the water, is that coming from only oil and gas production?
correct. Yeah, all these samples are coming from production wells, and so within the specific production well, I tried to aim for the ones that are only perked or focused in a single formation so that we are able to get those specific data points across the map. Because whenever you get into multi-zone curves, you get into disposal units and you're getting into those aggregates, everything that's mixed up and it's always lower. So
has there been a time when production has ceased or shut in?
Yes.
Where does that mean that your operations and also has stoppage?
Yeah, so back when COVID started on our facility in Ellis, a couple of those companies out in Ellis County did shut down because of the whole decline in the oil prices and everything. And so that facility did have to turn off for about a month. In our algal field, with Mississippi being such a high water producer and in comparison to the hydrocarbons being produced, that has steadily declined. So whenever a strong well is a higher water producer and it gets converted from an ESP well to a pumping unit, that is noticeable within our production. But we're able to work with these operators to maintain a certain volume as high as they can do it, as well as what we're tied into. So back whenever these algal plants got turned on in 2014, we're only taking water from roughly 10 sections within the nearby area. Now that same location is taking water from about 300 miles worth of pipe that operator has. So we are reaching farther to maintain the volumes that we need to run at, and the concentration has changed during that time because of the waters.
And maybe to answer maybe approaching it from another way. It is one of the downsides of our model is we're at the whim of an operator and what they do with their wells. It's part of our business model going forward is looking at fields that are, close to the end of life, have watered out, and is it something that we want to take upon ourselves to take these wells that an operator might shut in because they're not economical on the oil side of things, but if we don't have to spend the capex to drill wells ourselves, if we can just take these wells and keep them going as a brine source for us, that might work economically for us. Right now we're not necessarily looking to get into the game of drilling and operating our own wells, just because thinking back to our first slide, all of our capex and opex goes into the plants, and leaving the opex for operating a well to the operators themselves economically works great for us right now. But we are thinking down the line because we know that these wells aren't going to produce oil or gas forever, and they will get shut in, and then we will lose our brine stream.
And same thing, with the iodine being a commodity price, there are going to be times when that drops way down low. So we're needed to maintain a certain cost per kilo so that if the market ever does drop down, we can still ride it through. Like that's happened a couple times over the past 20 years, and we've been able to ride through those times as long as we're able to keep those costs low. But whenever we do take on the idea of drilling, maintaining our own field, our own wells, that definitely has been a consideration as far as that project goes. But we're still.
Is the iodine to chlorine ratio to produce brine similar to that of seawater?
No, because each formation has its own characteristic. And so kind of like what Andrew was saying on the correlation between the iodine versus everything else you're able to find, easily measured within the water. You have like the Cherokee formation where the chlorides are a little bit lower, but the iodine's still high. And then there's another field where the chlorides are a lot higher and the iodine's higher, or another field with the same chloride level and iodine's lower. It's very formation specific, and there's no general correlation between these different formations.
What's the concentration of iodine?
At roughly about 2 to 5 ppm.
So you're sitting in enrichment at the producing zones of about 100.
Exactly, and whenever we're looking into the fossils, we're kind of looking at those filter feeders, those bioconcentrators within the carbonate factor. Kind of like on that flaky environment. That's the thing that we're chasing. We both have our different opinions on where it's coming, so that's always fun to debate here.
Yeah, and there's a loose correlation. I mean, iodine, we see it in the Permian Basin at not quite the elevated levels that we see here, but a highly productive carbonate system. Iodine's been produced in Michigan out of the Pinnacle Reefs. So again, there's another carbonate type system where iodine is available. We don't see it very in other basins that we've looked at that are more sandstone terrestrial based type systems. We're just not really seeing it. The thing that contradicts that there, but is water being moved from somewhere else in the basin is in the Woodford Trench, producing from those marrow sands. It's a little bit different of a system where you see that enrichment, and it's not necessarily directly coming from a carbonate reservoir, but it is surrounded, I guess. So could it be coming from elsewhere, being moved from deeper in the system or laterally? Yep.
Curious if you considered a hydrocarbon source for this, because let me give you a little background on this. Hydrocarbon fluids come from the basement,
Yep.
and the way that the sedimentary section communicates with the basement is through basement. And I can tell you, if you're using the Oklahoma Geological Survey's full map, even what they coded as basement faults, and actually basement faults out there. That's not correct.
Okay.
Because you've got all kinds of induced seismicity out there, which is due to basement faults.
Yep.
So the fact that these bodies are constrained, they're not ubiquitous, they're not covering the whole county. They're local, they're very local bodies. And that to me suggested, but that's, I'm just throwing it out there as another possibility. Because when you look for exotic elements, you oftentimes go back to hydrothermal fluids.
Yeah, definitely thought about it, and need to think about that more. I would maybe think about it more that the those faults are acting as conduits for water that's sourcing from elsewhere. Before I worked here, I was doing critical mineral research at NETL, and critical minerals were highly related to hydrothermal fluids and or volcanic ash falls, or some sort of intermixing between the two, where you've got hydrothermal fluids that are then coming in contact with element-bearing volcanic ash beds, which is something that, at least on the iodine side, doesn't seem to quite correlate. It works well with lithium and other critical minerals, but it's definitely something that we need to investigate a little bit further.
And finding access, permissions to get those samples has been few and far between. I sent out a couple of hits, but they never came back to me. So if you know of anyone that would like to, yeah.
When I think of high water cuts, of course, in this that you're in the Permian, you've mentioned, but Southern Oklahoma has all the big floods where they're moving lots and lots of water. You got much data down there?
Yeah.
Show them like Meramec, show them.
Yeah, the farthest south I've gone is into Stevens County and south of Chickasha area. And so there's a couple pockets that are of interest, but the overall total mix of the water has been around that 60 to 80 ppm in the region that I was testing. And but moving outside east or west of that location I haven't had much.
Would you be interested in talking to the Ardmore Society and seeing if you could rally up some interest there? There are a lot of operators with a lot of 98% water catchment floods.
So the problem with floods is if you're introducing a lower concentration brine, and even it's something that we think about and consider a lot, especially now with the reuse of frack water, is if we extract the iodine and then that water goes back into the system, you're effectively diluting your stock water. So up front it would be probably very lucrative, but if you over time, if you continue to add zero concentration iodine to a system in a flood, you're going to start producing from fully extracted.
You just want your injector to be weighed out in
Yep.
different formation.
Yep.
After the water goes through the plant, is this composition change very much? And how much water can the plant handle a day?
So our typical facilities are designed to take between roughly 5,000 up to 25,000, or more optimal that 15 to 20,000 barrels a day. With the iodine removal process within the facility, we are replacing chloride. So with chlorides already being high, especially in Mississippi, it's negligible difference that the operators see. So it's the same water back minus the iodine, and we are neutralizing that to bring it back up. Most of the operators we're working with are requesting a 6.5 pH, and so that's what we target to return the water back to them. And it's cleaner because we're removing the oil and all that stuff. Better control that water.
We do our best to give the water back as close to how we got it minus the iodine.
Yeah, I have a question about your injection. injection well, is that, where you're the owner and operator, it's on your facility?
No, we partner.
Yeah, well, the injection wells still belong to the oil guys, especially in the static and at all the facilities we're at minus Iodine, we're on their disposal. So within their 6-pack, that's where we loop their water from their system into ours. And once we remove the iodine and neutralize the water, we return back into the next set of tanks within the 6-pack, and then that disposal continues on to either inject the water downhole at their injection, or they're sending over the pits for the reuse.
The way our contracts generally work is we take liability ownership of that water when it enters our system at a transfer point, and then it returns to the operator when it exits our facility at that custody transfer point. So we take liability of that water if there's a spill or anything like that while it's through our system, but we're basically just borrowing that water in the short time it takes to leave their tanks, come into our tanks, go through our towers, and then exit back out into their tanks.
So
Class 2 at the disposal of, is that classified as the
Class
2? Or is it class
Exactly.
1 commercial?
all these disposals are class 2, and we do not interfere with the classification of the injection wells. So so the oil operators are still able to do what they need to do without any impact from us. And on a typical 15 to 20,000 barrel a day facility, we're continuously running. So that one barrel of water that starts from the SWD goes through our process and gets returned back. We're typically holding on to that barrel on average 15 minutes. And so it's a very quick, continuous process. And once everyone's up to speed,
There's no impact on
no interference, no impact on them. And if we do have to shut down for any reason, then we have designs that they can bypass and continue on with the process with no interference of their operations. If they have to shut down and do that, well, that's going to impact us. We can't avoid that. But as far as us impacting oil operations, if we have to shut down, very good to go.
Taxes and royalties, are they similar from what they are in the hydrocarbons, or the royalty owners getting paid for this?
Yeah. We do a royalty program with surface and mineral owners, because there's no clear definition of how iodine has been classified within the OCC. So we're just trying to make the best guess of how to handle it until the courts actually make a definitive decision. So we take the total royalty and split between surface and mineral owners, and we take out our own iodine releases. So this is not a responsibility of the oil guys. We have our own independent leasing program that's separate from them, so that we're responsible, and it holds the oil guys, what's the word? Not responsible.
And the lithium, you had mentioned lithium and Arkansas and such as that. Are you getting many lithium readings on your stuff? Have you got lithium maps too, or those are only anything?
We don't have enough data to generate the same quality of maps that we have, but we, within the last year, I've been working with our chemist in Kentucky to generate this data set. So we'll soon start to be able to generate the maps to identify lithium and all the other performance that would be an economic benefit. And so we are developing those trends right now, just having those developed yet.
I don't think it was maybe not clearly stated. So we have two methods of testing. One is the bench test method, which is the quick and easy. It's only looking for iodine, but then our parent company in Kentucky has a ICP-MS machine that we ship samples to them to do further analysis. So there's the quick and easy method where we can just track iodine. We get those results back, within a week or two. We can push, 100 samples through real quick. It's when we start to dig into the other elements that, it's a little bit more involved, takes a little bit more time. And we're sharing that machine with our parent company who's using it for their own purposes. So we have to get in line for that as well.
So is iodine currently classified as a critical mineral by USGS or WTA?
It doesn't fall under the critical mineral, at least to my most recent knowledge.
So there's some discussion about maybe expanding the list of this current administration. Is there opportunity there? What does that do for products, I guess?
I haven't.
Yeah, I haven't
heard much about how iodine would fall into that category. That's all new, and unless you've heard anything, I'm going to leave that to my boss, Boris. He loves these questions. But we can get back to you on that one.
Yeah, that's all still fresh. We haven't put a lot of thought into it. And I'm not sure how that would really affect us at this point.
Yeah, just to answer his question just a little bit, during the Trump first administration, the uranium industry was in the dumps and then it went to the government for assistance. And they were playing that angle of getting uranium, classifying, subsidies or regulations, something, to get production, the lines were just shut and they get production.
If that's it, thank you so much.
All right, well, thank y'all very much. We hope to see y'all at some more of our April events. Here you go.